All questions are meaningful.
So at the very beginning, we drew these, like, we called it a line arrangement where we had blue, dotted, and red.
Yeah.
I kind of, like building these tables that we did before. Can you explain how that line arrangement stuff is
Yeah, it's the fancy name of it is called incidence geometry, which isn't actual geometry. It's just a recipe. Just like we built this recipe. So how would you do this? You would have a collection of points. I call them all the A's and B's. So if I grouped, how many points do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I started making sets of these 9 points. So one of those sets is A, B, C. One of them is little a, little b, little c. One of them is x, a, b, and so on like that. So you're creating, from this big set, you're creating a lot of subsets. And then you make the rule that all of these sets have to tell you something geometrically. And this is how you could build this kind of, this is called the Fano plane. And you could build this by a combinatorial recipe, but never figure out how to realize it in Euclidean geometry. So actually, really great question. So it's thinking about just like the study of finite sets, which is a combinatorial thing because you're just counting objects there.
The idea is that so like here we kind of had the Cartesian plane as a reference frame. Like when we drew a line, we had an idea of what line meant in the plane. But the other one, we might have like a different definition of what a line is that isn't dependent on being in a plane kind of thing.
Yeah, that's what I said, where I said, what do we mean by lines and what do we mean by planes? And this, like, you could just keep making up different rules and build your own geometric spaces. Like, you don't necessarily need you could start, like, for example, you could say, well, I believe in the real plane, or I believe in the complex plane. You can make all those rules, but then you could also just say, well, I just want to count a bunch of things and see what I learn from it. And so I'll just show you some more pictures. Sorry, because I put so many in the talk. It turns out that there are a bunch of arrangements that can't be drawn in the plane. And here are 3 of them. This one's called the Fano arrangement. This one's called Mobius-Cantor. And this one's called Cantor. And it turns out that you can't do this with arrangements of lines. But if you did arrangements of lines and circles, then you could do these. So maybe lines changed. And then we kept the definition of plane. Or the definition of plane could now be under incidence geometry. Did that go? I'm sorry, I was maybe talking a little above you. Literally, because she's a couple rows above. Oh.
Anybody? I would like you to say one sentence, if you can. How is Braids connected? Where is Braids in line?
Yeah, I'm so sorry. Okay, so it turns out that if you have these pictures that look like this, you can take a comb to it. And if you take a comb to it, you create this picture, which is called a wiring diagram, which is sort of like an electrical thing. Now, if you look at this, this looks like it would be a braid, except for one small detail. Every time the braid passes over itself, it's a point instead of going over. So I should have said that all the way at the beginning, because these are like what happens if you take a braid and shine a flashlight to it and look at its shadow. So these are like the shadows of braids. And then if you're really complicated, you can even braid these complicated things. So you can have points and braid information in there. And those are called complex wiring diagrams. Is that enough? I'm sorry.
Line arrangements are somehow flowing into braids.
Is that related to, like, so if we add in a classical crossing of, the braids, is that related to the welded braid group? Or is that
I don't know all the names. I do know that I study knots, and these are sometimes called singular knots. So there's a way to turn braids into knots. And the way is you made a braid, and now you want to join your bracelet. So you take this side, and you just connect them up to each other. But we do it in a rule that this line connects up to here, and this line connects up to here, and so on. We do that each of the way down. And so what we get is either a knot or a link, which is several different components linked together. And the people who I know who study these, like Carmen Caprau at Cal State University, Fresno, she calls them singular knots, which is like what happens when you look at like the shadow of the braid. You have what's called a singularity. So she studies what happens if you are allowing crossings, or allowing like the braiding kind of thing to happen, but also you're allowing these things to happen. I don't know what welded braids are, so maybe that's the same thing. I don't know, I'm sorry.
It would have order too, so it would be a little different, but yeah.
Sorry, can you repeat what singularity?
Yeah, mathematicians like to use this word, but so do like people who write sci-fi stories. A singularity, oh, so crazy. So singularity is really like an intersection, because if I am standing on this thing, we talked a little bit about like topology. If I was a tiny little ant, I'd be walking across this thing and I would think the world is a one-dimensional thing. But then I got up to this weird point and it'd be like, what, is this a gateway into another world? Like, look, the ant can now continue or can go on this other thing. We call it a singularity. There's problems with derivatives there, so if you want to think back to calculus. Is that enough on that? This is like, you could take a book out from the library called Singularity Theory, so I did not do this justice.